All right, hello everyone. I wanted to make a hopefully somewhat short and sweet video reviewing the breakdown of glucose aerobically to produce ATP. So we know that for every one molecule of glucose, we produce a total of 32 ATPs, 33 if we were to start with glycogen. But where exactly are all of those ATP coming from? So that's what we're going to look at here, is where exactly along the way are we producing the ATP? How does this happen? But before I actually get into the steps here, I just want to take a quick step back and sort of review what are we even talking about in the first place here, okay? We are looking at the aerobic breakdown of glucose. So going back to our slides here, we know that aerobic energy production, aerobic ATP production, is the process of oxidative phosphorylation. And we know that we can use carbohydrates, we can use fats, or even proteins to sort of go into this system and produce ATP aerobically. However, we are going to focus on carbohydrates, specifically glucose for this example. So skipping ahead here, this is sort of the overview of aerobic metabolism in general, right? We know that aerobic metabolism includes the Krebs cycle, where acetyl-CoA goes through a series of chemical reactions, and the electron transport chain. But in order to start the Krebs cycle, we need to start with acetyl-CoA. And we know that carbs, fats, and proteins can all be converted into acetyl-CoA. But again, we are focusing on carbohydrates, specifically glucose. So the question is, how do we produce ATP from glucose aerobically? Well, when we are starting with carbohydrates, basically we're starting with pyruvate, right? When we break down glucose, that's how we get the pyruvate, right? So in order to have that pyruvate to be converted to acetyl-CoA, we need to first have the process of glycolysis, okay? So when we're looking at the aerobic breakdown of glucose, step one is going to be glycolysis. First, we need to break that glucose down into 2 molecules of pyruvate. Then those pyruvates can get converted into acetyl-CoA. And then once they're converted into acetyl-CoA, they can go through the Krebs cycle, and we're going to start producing things that are going to lead to ATP being produced aerobically in the electron transport chain at the last step. So this is what I'm going to go over. I have a little simplified flow chart here to basically run through exactly where all of those ATPs are coming from. At each step, but totally simplified. We're not going to be talking about any of the enzymes, anything like that. Just short and sweet. Where is it coming from? Where, when is it coming from? Whatever. And what is our total? Okay. So again, before I even go through this, where are we starting from? We're talking about glucose. So first, we have to break the glucose down into pyruvate. The pyruvate will get converted to acetyl-CoA. Acetyl-CoA goes through the Krebs cycle, and then we have the electron transport chain, okay? All right, so here we have our little flow chart, okay? Starting with 1 glucose. Step 1 is slow glycolysis. So going back to the slides here, that's going to be glycolysis, right? We know that through the process of glycolysis, which is the breakdown of glucose into 2 molecules of pyruvate, we produce 2 ATPs and 2 NADH, right? 1 glucose gets split into 2 separate molecules. We end with those 2 pyruvates, 2 ATPs. So here we have that. Let me move this over a little bit. There we go. So step 1, here's our glucose. We split into 2 molecules of pyruvate, and in the process, we produce 2 ATPs and 2 NADH, okay? So in our step 1 glycolysis, what's going on here? Well, first of all, just as a side note, this is occurring in the cytosol, okay? You want to know where things are occurring. So this is happening in the cytosol. Glycolysis happens in the cytosol. And when we end with our 2 molecules of pyruvate, if oxygen is present, which is what we're talking about here, both the pyruvates and the NADH that we make will be shuttled into the mitochondria to get converted to acetyl-CoA and continue with the rest of the steps. Okay, so step 1, glucose gets converted, broken down into 2 molecules of pyruvate. Along the way, we make 2 ATPs and 2 NADH. Okay, so step 1, what is our ATP tally? Okay, and by the way, before I even go over this tally, the only 3 steps that we need to tally anything are step 1, step 2, and step 3. Glycolysis, the conversion to acetyl-CoA, and the Krebs cycle. Okay, so anyway, step 1, again, to just go back again. Step 1 is the breakdown of glucose into 2 molecules of pyruvate. We make 2 ATPs, 2 NADH. So what is our ATP total? Well, 2 ATPs and 2 NADH, and every 1 NADH is equal to 2.5 ATPs. So 5 from NADH, 2 regular ATPs just produced along the way, 7 ATP totals from step 1. Step 2, each of those pyruvates is going to be converted to acetyl-CoA. So I actually have the pictures here, right? So right here, this is step 1. Glucose is converted to 2 molecules of pyruvate. We make 2 ATPs and 2 NADH. Now, each of those pyruvates are going to get converted to acetyl-CoA in the mitochondria if oxygen is present, which is the example we're using here, right? Slow glycolysis, where oxygen is present and they go on, right? The pyruvates are not getting converted to lactic acid in this example. So here's where we have the conversion, okay, of pyruvate to acetyl-CoA, right? This is what we see on the slides, and we produce 1 NADH along the way. So simplified, here's step 2. Each pyruvate is converted to acetyl-CoA, and we make 2 NADH along the way, 1 for each pyruvate. So here's our total ATP output for this step. Well, we didn't make any just regular ATPs, we only made 2 NADH, but each NADH is equal to 2.5 ATPs. So our total ATP output from step 2 is 5 ATPs total, right? Which came from those 2 NADH. We also produced some CO2, but that's not adding to our tally, so we're not going to focus on that. So far in step 1, from 1 glucose, we made a total of 7 ATPs from these 2 things that we made here. In step 2, we produced 5 more ATPs now, right? Each conversion was 1 NADH, and 1 NADH is 2.5 ATPs. So for 2 NADH, it's 5 ATPs. Now, each one of those acetyl-CoAs are going to go through the Krebs cycle, right? Here's where we're talking about right here. So each acetyl-CoA goes through the Krebs cycle, and through that process, we produce some NADH, some ATP, some FADH, and some CO2, which again, we're not really talking about. Okay, so what is our net production of ATP in step 3, the Krebs cycle? Well, we have to first acknowledge that all of this is happening twice, right? Just like we had to do the conversion twice because we had 2 pyruvates, now each acetyl-CoA is going to go through the Krebs cycle. So there's 2 Krebs cycle turns happening for every 1 glucose, right? So that's what we have here. Each acetyl-CoA is going to go through the Krebs cycle and produce 3 NADH, 1 FADH, and 1 GTP, which is 1 ATP, and we also produce some CO2, right? But all of that is doubled because we're starting with 2 acetyl-CoAs. So what is our net total ATP from step 3? Well, we gotta tally all this stuff up here. Well, we have a total of 6 NADH, right? 3 for each molecule of acetyl-CoA. But we know that 1 NADH is equal to 2.5. So the 6 NADH is actually equal to 15 ATPs. We produced 2 molecules of FADH, 1 for each turn of the Krebs cycle, and 1 FADH molecule equals 1.5 ATPs. So for our 2 FADH that we produced total, we have a total of 3 ATP produced. We also produced 2 molecules of GTP, and each GTP is equal to 1 ATP. So for the 2 GTP that we produced a total of 2 ATPs. So our grand total of 20 ATPs for step 3 comes from these 3 things, okay? So far, we've produced from 1 molecule of glucose 7 ATPs through glycolysis, 5 ATPs when we converted each of those pyruvates to acetyl-CoA, and a total of 20 ATPs as each of those acetyl-CoAs went through the Krebs cycle. Now, step 4 is the electron transport chain, right? If I go back here, that's going to be step 4. So step 4 is the electron transport chain. This is also occurring in the mitochondria. This is where all the ATP is made in the aerobic system, right? This is that picture from the slides that we were talking about. So this is where all of the NADH and all of the FADH that we produced and all of the other steps bring those hydrogens. Remember, they're little hydrogen carriers participating in oxidation and reduction. They're dropping their hydrogens off and picking it up in other places. So this electron transport chain is where all of the NADH and FADH that we produced in the other steps come along, drop off their hydrogens to create this hydrogen gradient. And as you know, it's the hydrogen gradient that powers the ATP synthase, the enzyme that makes ATP. Right there is where all of the ATP is being made aerobically. Yes, we made, a couple regular ATPs along the way, but for the most part, all of the ATP produced aerobically are coming from all of those NADH coming along and giving their hydrogens here, okay? So this is, again, where the NADH and the FADH are equal to 2.5 and 1.5 ATPs, right? For every 1 NADH that comes along and drops off its hydrogens and electrons, it ultimately leads to about 2.5 ATPs being produced through this system, okay? So that's why we have to tally up all of the NADH and FADH along the way, okay? But anyways, as I was saying, and as you may know from the lecture, this is where the NADH or the hydrogen gradient powers the ATP synthase. ATP is made aerobically, and then this is where oxygen comes in as the final hydrogen acceptor, right? We need that gradient where the hydrogens flow from the area of high concentration to low concentration. Right? When the hydrogens flow through down their concentration gradient, that's what's powering the ATP synthase to create ATP. So we need that gradient of the high concentration to low concentration so the hydrogens will flow in that direction and flow through the ATP synthase. But if all of the hydrogens just flowed through and just stayed there, well, then there would be a high concentration down there too, and there wouldn't be a concentration gradient causing them to flow from high to low. So we need to get rid of that hydrogen down there so that we can keep that gradient going. So this is where oxygen comes in. Oxygen comes in and combines with that hydrogen and forms water. And then the water's just in the cell, right? We have water all over our bodies. It's fine. But we got rid of that hydrogen, the gradient can keep going, and we can keep producing ATP aerobically, okay? So again, the electron transport chain is where we're producing all of our ATP aerobically, right? Again, we made a couple ATPs along the way, but for the most part, the whole process of all of this was making a whole bunch of NADH and FADH and stuff like that, right? Because the NADH and the FADH are what are ultimately leading to the bulk of the ATP produced, okay? So we don't have to tally up anything for step 4 because we've already tallied up all the ATP from the NADH and FADH in all of these previous steps, right? We already tallied all of them up for each step, right? So the grand total we made 7 ATPs in step 1, right? 2 regular ATPs and 2 NADH, which led to 5 ATPs, right? So the 2 plus 5 was 7 ATPs total. Step 2, we made a total of 5 ATPs, right? We made 2 NADH, each NADH is 2.5, so for a total of 5. Step 3, we made a total of 20 ATPs. We made 6 total NADH, 1 FADH, 6 total NADH, 2 total FADH, 2 total GTPs, which are ATPs, and some carbon dioxide, but we don't care, right? So all of those things tallied up end up giving us a total of 20 ATPs. So our grand total, right? And then all of that stuff goes to the electron transport chain, and that's where the ATPs are getting made that we tallied, right? So the grand total for every 1 glucose through all of these steps ends up being 32 total ATPs for every 1 glucose produced aerobically. Okay, so this is where it's happening all along the way. Now, I didn't really say, well, why is it 33 if we started with glycogen? Well, very simply put, in step 1, we actually will produce 3 ATPs in this step if we start with glycogen. Okay, we only produce 2 ATPs total if we start with glucose. But if we start with glycogen, we produce 3 ATPs total, right? So if we produce 1 extra one and we just increase all of our tallies, right? So step 1 has 8 instead of 7. That's how we get 33 for glycogen. Okay. So hopefully that made sense. If you aren't familiar with some of this stuff, it may be a good idea to sort of go through the lecture first before watching this video, but I wanted to sort of attempt to find a simplified way of breaking all of this down. So I don't know if you want to take a screenshot of this, chart or whatever. I'll, keep it here. Scroll down a little bit. Maybe I'll find a way to print it as a PDF or something after I make this video. But anyways, I hope this helped to sort of explain things a little bit when we look at this tally right here where we get our 32 ATPs. Where are they coming from? How are we tallying them up? And just what's going on. So yeah, as always, if you have any questions, please let me know, and I hope you have a wonderful day.